Okay, I want to explain a better way to solve flash drums, and this is the graphical method. And with our graphical method, or graphical solution, it's a much more quicker way to go ahead about solving them. These flash drums, where we want to find out what the concentrations and flow rates and so forth are. Takes a little bit to get used to on the first grasp because it's not as, I guess, intuitive, you might say, because we're not necessarily solving a bunch of equations, but we're using a graph to solve for what the various unknowns or various parameters are for a flash drum. So let me just write out our equation for a material balance. So that's our material balance there. And I can go ahead and take this equation and I can rearrange it. Let me go ahead and rearrange this and come up with an equation. And then so I'm going to just label this star, because this is such an important equation, the star equation. Or I could write this same equation as this. So it's in terms of a parameter called f, which I'll shortly define. And then f is going to be equal to v over f. So big F is the flow rate. Let me just quickly draw our flash drum here, and I probably should have done this at the beginning just to remind you what all these variables are. So we have F and Z, we have V and Y, L and X, and big V here is the flow rate of the vapor, big F is the flow rate of the feed, and little f is just a parameter which is defined as big V over big F right here. So that's our little f parameter. I could also write this equation as y is equal to negative q over 1 minus q times x plus 1 over 1 minus q times z. And in this case, q is equal to L over F. I'm going to call this one triple asterisk. So we have three different equations. They're basically the same equation where I'm just using different parameters. In this first equation, I have it in terms of F over V and L over V. In the second equation, I've eliminated F, V, and I've eliminated F, L, and V, and everything is in terms of little f, which is defined as the ratio between big V and F, or the fraction of the feed that becomes vapor. Or I have this third equation where it's defined in terms of Q, where Q is the ratio of L to F, or the fraction of the feed that turns into vapor. All three of these equations right here are very important, and they're known as the operating line. Write that here, operating line. And this is the general equation that we use, or one of these three different forms. Again, this is the same equation in three different ways. And we're going to use these three equations, or at least one of them, to go about solving this graphically, the graphical method. And so let me just point out a few things about this before we jump into more details, that each one of these three equations is of the form of y equals mx plus b. And you've seen equations like this before in algebra or geometry or some of your other classes before, math classes. This is just a straight line. So this is a linear equation. We can draw that as a straight line on graph paper. And all three of these equations are of the format y equals mx plus b. They just have different values, different values for m here, m, and this is b, b, b here, but we can draw these as straight line. And so when we use the graphical method, we're going to draw these lines as a straight line and use that to help us solve for a flash drum system like we have up here. The other thing I want to point out, just to remind you, each one of these three equations, all it is it's a representation or reformulation of the material balance equation. This is the material balance equation. Each one of these is just the material balance equation written in this format down here. So this straight line represents the material balances of a particular flash drum or a particular system. And you'll see that, depending on the system we have, for instance, if we have a L over V of one value, it may be a different L over V for a different flash drum, so the slope of these lines will be different depending on what the L over V values are right there. And the same thing with these slopes here and here. So every flash drum has a unique slope when we draw as a line following this y equals mx plus b format. And the same thing, every different flash drum system has a different b value right here depending on these parameters that go into it. So the idea behind this graphical method is that we're going to combine vapor-liquid equilibrium in the form of an XY plot with the operating line in order to solve for or design a flash drum. And the vapor-liquid equilibrium curve, again, shown here, that represents the data of the equilibrium between the vapor and the liquid that's coming outside a flash drum. Well, the operating line, or the equation for the operating line, it represents the material balances of the flash drum. So the combined solution will involve both an XY plot and the operating line. So again, the solution is a combination of the vapor-liquid equilibrium, XY plot, and the material balances, or operating line. So when we go ahead and solve it, what we'll do is we'll go ahead and draw on a curve like this XY plot, our operating line. Here's just an example of an operating line. So it's a straight line that represents the material balances, and where these two intersect with each other, that represents a solution where the vapor-liquid equilibrium constraints are satisfied and the material balance equations are satisfied. So this is a nifty way that we, just by drawing things on a nice graph chart, we don't have to worry about some of the messy mathematics of going about solving solving or designing a flash drum, where we might have to do some iterative guessing, or we might have to solve some difficult equations. We can just simply use this, the vapor-liquid equilibrium curve where it meets the operating line or the material balance line in order to find out the solution for our flash drum. And so let's look at an example of the steps of how we go through about solving that. All right, let's see how we actually put this all together to go ahead and solve a real problem using this graphical method, or solve a real problem related to a flash drum. Okay, so I have here a vapor-liquid equilibrium curve. This is just a water methanol mixture. So again, down here on the x-axis we have the mole fraction of liquid methanol. It's the more volatile component. Y-axis we have our vapor mole fraction of methanol. This is our vapor-liquid equilibrium curve right here. We just have the y equals x line for ease of following the curve and to help us draw everything. So the first step that we go ahead and do is number one. We go ahead and draw vapor-liquid equilibrium curve. In this case, I just plotted this up from some data that I found. I think I found this all online, but I made this plot in Excel, so I've drawn that. 2, we go ahead and draw operating line. So those the lines we were just talking about, we go ahead and draw that. And so let me go ahead and give you an example of this. So in this case, I might have z is equal to 0.4, L over V is equal to 1. So the slope, this line is going to be -1. So at this point, I just have to find right here. So that's the z equals 4. That's where y equals x equals 4. And then I have to draw this line here. Let's see if I can draw this straight. Something like that. So that is my operating line for a value where the feed value is 4.4. And the L over V ratio is 1, so giving me a slope of -1. And then step 3 is to find point of intersection. So find the point of intersection between those two lines here. So in this case, my point of intersection is that place right there. And then I go ahead and read this, and I get myself my y, my x values just by looking at that point of intersection. So in this case, if I'm looking at that, I'm looking at the liquid mole fraction of methanol is probably about 0.18, and the vapor mole fraction of methanol is about 0.64. If I wanted to get much more detailed on this, I'd probably use a ruler to measure it exactly, or I'd try to line up my lines better in order to get a better exact line here. Especially when I'm drawing my operating line on a real curve, like for homework problems or anything else, or when I'm really trying to design a flash drum, I definitely want to use a ruler. So you can get a nice straight line. So this whole setup here is known as the McCabe-Thiele diagram. And this, again, this method is simply drawing our vapor-liquid equilibrium curve, drawing our operating line, which is just a graphical representation of our material balances. It tells us information. We have information about our feed and our ratios of different liquids or vapor coming out of our flash drum. And then finally, where those two intersect, this point right there, that tells us our values of y and x coming outside of our flash drum. And that's the whole procedure for the McCabe-Thiele method, or graphical method for solving a flash drum.